Hey, how's everybody doing today? I had a little bit of time to kill today, so I thought, yeah, it would be nice to have one final little rally and do one final video on power factor correction. This one, well, it's going to be short and sweet and to the point. So let's get on with it. First, let's take a look at finding capacitance to fix power factor in general. This particular circuit, an RL circuit, kind of sums up most or the majority of the circuits, where you have any sort of basic inductor, whether that's a motor or a transformer or any sort of inductive load. Since it has a coil, it has inductance. And since a coil is usually made of a wire, well, the wire has resistance. And as we looked at before, this is basically an RL series combo. So it's kind of where you have to start. For power factor correction, what you're doing is you're allowing the capacitive power to cancel out the inductive power. If the two of them are equal, we say that the circuit is at unity. Unity is where the true power, P in watts, is equal to the ST or apparent power, or the total power of the circuit. There is no reactive power left over. The power in the capacitor will completely take care of or cancel out the power in the inductor, so that the true power, P, and the apparent power, S, are in unison, where P equals S or S equals P. We had already looked at the power curves. So when we apply a voltage, the inductive current lags behind, the capacitive current leads, and when we look at the powers for each of those, the reactive power and the capacitive power are at 180 degrees out of phase. This is what allows us to do our power factor correction. The capacitor will feed the inductor when the inductor needs power. The inductor will feed the capacitor when the capacitor needs power. If the two of them are equal, then our total reactive power will equal 0, where QL minus QC, if they're the same, will leave nothing left over. And it's at that point we say our circuit is in unison or unity. And that's what we'll be solving for today. So here's our first little circuit. We have an RL combo of 60 ohms inductive and 80 ohms resistive. It's hooked up to a 240 volt, 60 hertz supply. And we need to find a capacitor for unity. Again, unity is when the apparent power, the total power of the circuit, ST, equals the true power, P, power watts. So the first thing we have to do is we have to solve for a circuit with our RL combo. We need to find the two powers here, because S is going to equal to P, and then QC is going to equal QL. So we need P and QL. In order to get those powers, one of the easiest ways to do it is just find our current and multiply through. In order to get our current, well, we just solve it like we used to solve RL series circuits before. Find your Z. Once you have your Z, you can find your current. Once you find your current, square it, multiply through by your ohms, and that'll give you your respective powers. In this case, we end up with 460 watts and about 345 bars. Sometimes the problem asks you to find the total apparent power, so you know what the power is before. You can vectorially add them, or you can use ETIT to get ST. So before we put a capacitor in this circuit will draw 2.4 amps. It will have 576 VAs of total apparent power. This will result in an 80% lagging power factor, which means our current is at minus 36.86 degrees. In order to find out our capacitor, we need to let QL equal QC. We just can't put in the same amount of capacitive reactance, 60 ohms, as our inductor, because the inductor does not get the full 240 volts. It's in series with the resistance. So it's a series parallel combination. But if we let the capacitive power equal the reactive power, then those two powers will cancel each other out. So that's what we do. We let QL equal QC, and that is, in this case, 345.3 VARs. Now our capacitor is hooked up in parallel, so it gets the full whack 240 volts. Using voltage squared over our power, we can get our XC, which in this case works out to 166.81 ohms. Once you have your XC, you can rearrange your capacitance formula for capacitance, and that works out in this case to be 15.9 microfarads. So we would need about a 16 microfarad capacitor in order for this circuit to be at unison. Again, unison is where our total apparent power equals our true power, which in this case is 460 watts, which we calculated earlier. So our power supply, E, at 240 volts, only has to supply 460.8 watts worth of energy. So that will change our corrected current. Our current at unity is just P over E, which in this case drops the current down to 1.92 amps. Since we are only feeding the true power of the circuit, this current is at 0 degrees. It's a similar approach when we're finding capacitance fit to find the power factor, when we're giving the horsepower of the load and the power factor of the load. Let's take a look at one of those. So here we have a simple motor circuit. We have a 20 horsepower motor hooked up to a 240 volt 60 hertz supply, and the motor operates at a 65% lagging power factor. Now here in North America, motors are usually rated in horsepowers. That's the amount of work that's actually being done or going out of the circuit. Any power that's lost, well, that's true power in watts. So the first thing we have to do is we have to convert our horsepower into watts. The conversion factor for horsepowers to watts is that there is 746 watts for every 1 horsepower. So you take your 20 horsepower, multiply that by 746 watts per horsepower, that leaves you with 14,920 watts. Now that we have our true power, we also have our power factor. Now we know that power factor is the ratio between true power and apparent power. Since we have the power factor and the true power, we can actually calculate our total apparent power for this circuit. Just take your true power, divide by your power factor, and that means that the circuit has to supply 22,954-ish volt amps. That's the total energy that our source has to supply. Now that we have the total apparent power, we can get our total current, where our total current is equal to apparent power over our voltage, which in this case means that the motor will draw 95.64 amps. Taking the arc cos of 0.65, you'll also find out that it has a lagging angle of 49.46 degrees. Working with the subtraction formula of Pythagorean's theorem, we can take the difference between our apparent power and our true power, vectorially, and come up with our inductive reactive power for this motor, which in this case is about 17.4-ish kVARs. Now in order to do our power factor correction, we're going to have to add a capacitor to the circuit. As we did before, we will solve for unity power factor, where once corrected, the power in the capacitor will cancel out the power in the inductor. And the true power, P, will be in unison with our apparent power. So in order to do that, we have to let our capacitive power equal our inductive power, which we said was 17.4 kVars. Again, using our old power formula where P is equal to E squared over R, we rearrange that so that our XC is equal to E squared over the power. This results in 3.3 ohms of capacitive reactance for our capacitor. When we multiply it out, we find out that that results in a 803-ish microfarad capacitor. We can now find what the corrected current will be for this circuit. Again, since our capacitor is feeding our inductor, our source only has to supply the true power portion of the circuit. Because at unity, our total apparent power equals our true power, which we calculated out to be 14,920 watts. We take our 14,920 watts, divide that by 240 volts. That results in a current of 62.166 amps. And since it's at unity, that current is at 0 degrees. I hope you found this helpful, and we'll see you the next time.